Hello everyone. Today we are going to discuss with you about energy in simple harmonic motion. So you see how energy in simple harmonic motion can be defined. Energy in simple harmonic motion. Energy in simple harmonic motion. In simple harmonic motion. Simple harmonic. Simple harmonic motion. How it can be defined and how we get the graph also of simple harmonic motion. So you see here we are going to define how energy in simple harmonic motion acts. Both kinetic energy and potential energies of a particle in SHM vary between 0 and their maximum values. We know that. We know that. We know that. We know that both kinetic energy, kinetic, both kinetic and potential energies, kinetic and potential energies and potential energies of a particle, potential energies of a particle in SHM, simple harmonic motion, vary between 0 and their maximum values and their maximum values and their maximum values. We have found now first of all we find the kinetic energy of a particle. For that we have to know the simple equation, that is displacement versus time. So the equation of displacement, the equation of displacement versus time, displacement versus time can be written as x is equal to a cos omega t plus phi, where phi is the initial phase. Now, if we want to define kinetic energy, we have to find the velocity. So, to find velocity, you know that v is equal to dx of dt, dx by dt. This is the velocity. And if you differentiate this equation, we are getting the value of differentiation of cos theta is minus sin theta. There is minus a cos is sin omega t plus phi, and again this omega will come here. So we are getting a minus omega a sin omega t plus phi. This is the velocity. Now if we want to find the kinetic energy of a particle, then kinetic energy can be defined as half mv. We know that kinetic energy is equal to half mv square. So applying this here, we are getting the value here half into m, and this is the expression for velocity, that is minus omega a sin omega t plus phi, omega t plus phi, and if we multiply twice, then we are getting the value half m omega square a square sin square omega t plus phi, right? Half m, and we know that in the previous section we found that k equal to m omega square. K is equal to m into omega. So we already found that omega square equal to k by m. So here we can find that half k square, a square, sine square, omega t plus phi. This is the kinetic energy. This is, you can rate it here as equation 1. So what we find that the kinetic energy also a periodic function of time, being 0 when the displacement maximum and maximum, and maximum when the particle is at the mean position. So here we find that the kinetic energy is 0. The kinetic energy is 0 when the displacement is maximum. Kinetic energy is 0 when the displacement is maximum. When the displacement is maximum. We know this one. When the displacement is maximum, kinetic energy is 0. The kinetic energy is 0 when the displacement is maximum, and kinetic energy is maximum, and kinetic energy is maximum when the particle is at the mean position. When the particle is in the mean position, right? Now you see here that the kinetic energy is 0 when the displacement is maximum, and kinetic energy is maximum when the particle is in the mean position. Since the sign of V is immaterial in kinetic energy, the period of kinetic energy is T by 2. You have to remember that since here since the sign of V is immaterial, since the sign of V, the sign of velocity is immaterial in kinetic energy. Immaterial in kinetic energy, the period of kinetic energy is T by 2. The period of kinetic energy is T by 2. So this is a form of kinetic energy. Now if you want to find the potential energy, what is the potential energy of a particle? This is the kinetic. So we got the kinetic energy as the value of half k a square sine square omega t plus phi. This is the kinetic energy. If you want to find the potential energy, what is the potential energy? 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 What is the potential energy U of a particle? U of a particle executing simple harmonic motion. Executing SHM, simple harmonic motion. We have seen that the concept of potential energy is possible only for conjunctive forces. We have seen that The concept of potential energy, the concept of potential energy, the concept of potential energy is possible only for conservative forces, only for conservative forces. The spring force F equal to minus kx, the spring force F equal to minus kx, F is equal to minus kx is a conservative force, conservative force. The spring force equal to minus kx is a conservative force with associated potential energy, associated potential energy. So U is equal to half kx square, half kx square. Hence the potential energy of a particle executing simple harmonic motion is hence the potential energy of a particle executing simple harmonic motion is Ux depend on x is equal to half kx square, and if you replace x is equal to pi a cos omega t plus phi. Therefore, we find the value of Ux as half kx square means a square cos square omega t plus phi. So this is equation number 2, right? Thus the potential energy of a particle executing simple harmonic is also periodic with period t by 2. Thus the potential energy of a particle executing simple harmonic motion is also periodic. With period t by 2, with period t by 2 being 0 at the mean position, being 0 at mean position, and maximum at the extreme displacement, and maximum at the extreme displacement, extreme displacement. So what we get here, that so we can say the total energy, thus the total energy E of the system is equal to kinetic energy plus potential energy, right? So we are getting the value for kinetic energy as half k A square cos square omega t plus phi, omega t plus phi, and potential energy is plus half k a square, half k a square sin square omega t plus phi. So here we are getting, if we take common half k a square as common, then we are getting the value cos square omega t plus phi plus sin square omega t plus phi. And in trigonometry find that sin square theta plus cos square theta is equal to 1. So we are finding that is equal to half k into a square. Why? In bracket you can write since cos square omega t plus phi plus sin square omega t plus phi is equal to 1. We know this is a trigonometrical identity. So we are getting is equal to half k square. The total mechanical energy of a harmonic oscillator is thus independent of time as expected for motion under any conservative force. So the total mechanical energy, the total mechanical energy of a harmonic oscillator, is thus independent of time, as expected for motion under any conservative force, under any conservative force. The time and displacement dependence, the time and displacement dependence of the potential and kinetic energies. The time and displacement dependence of the potential and kinetic energies of a simple harmonic oscillator, is given below. So here we are going to draw the graph of kinetic and potential energy. So here you find that we are drawing the kinetic and potential energy here. So we are getting the value here as this is 0 to t. We will find this one. It is 0 and it is t, and in between it is t by 2. So here you find that the energy will be like this, right? So first we will find the kinetic energy. The kinetic energy is 0 at the extreme position, right, this point. So we will find a equation like this. the kinetic energy will be like this. To draw a little bit more. Now we are finding the kinetic energy like this. It will be like this. Maximum, and at t by 2 it will be minimum. And again it will be maximum, and at t it will be minimum. This is t, right? And this, so you see here, this is the kinetic energy. Kinetic energy, right? And if we find the potential energy, then we are getting the potential energy here as right. This is kinetic energy dependent on time, is here, right? And if we find the potential energy, then we get the potential energy here like this. So you'll find this here as this is the potential energy, and potential energy is also dependent on time. This is potential energy U, and here is the U is also dependent on time, but the total kinetic energy is independent of time, right? So here you find that E, the total energy, is equal to kinetic energy dependent on time plus potential energy dependent on time, but the total energy is independent of time, right? So here you see that this one is repeated, this graph is repeated here. So the frequency of kinetic energy will be twice, because you see this is repeated once again. In the same case of potential energy is also. So this is the total kinetic energy, right? And that is kinetic plus potential energy. And if you find the graph for displacement, then we will find like this. So this is the graph for that. This is like this one, and there is another like this one. So what you find here is that the kinetic energy, this is the kinetic energy, that is from plus A to minus A. This is the kinetic energy. This is kinetic energy K, depend on X, right? And it is minus A, this is plus A. The kinetic energy is 0 at minus A and plus A, but at the mean position the kinetic energy is maximum. In case of potential energy, it is like this. In case of potential energy, it is like this. At the mean position, the potential energy is 0, but at the extreme position, the potential energy is more, right? So it is Ux. So we are finding this line as Kx plus Ux. So this is the kinetic energy, potential energy, and total energy as function of time. You see, this is function of time of a particle in SHM. The kinetic energy and potential energy both repeat after a period of t by 2. The total energy remains constant at all t. Here we find that the total energy remains constant at all t or x. So the total energy is constant, but the kinetic energy and potential energy is variable, right? So what we find, what we observe here is that we observe that both kinetic energy and potential energy, both kinetic energy and potential energy in SHM, simple harmonic motion, are seen to be always positive, are seen to be always positive, always positive. Kinetic energy can of course be never be negative. Kinetic energy can of course be never negative, be never negative, since it is proportional to square of the speed, since it is proportional to the square of speed, to the square of speed, Potential energy is positive by choice. Potential energy is positive. The potential energy is positive by choice. Energy is positive by choice. Positive by choice of the undermined constant. By choice of the undermined constant in potential energy. Both kinetic energy and potential energy peak. Both kinetic energy and potential energy peak twice during each period of SHM, of simple harmonic motion. For x equal to 0, the energy is kinetic. The energy is kinetic. For x, the energy is kinetic. At the extremes, that is x is equal to plus minus a, it is all potential energy. We know this one. In the course of motion between these limits, kinetic energy, in the course of motion, between these limits, kinetic energy increases. Kinetic energy increases at the expense of at the expense of potential energy, or vice versa, potential energy or vice versa. So we have a clear picture of kinetic energy and potential energy of simple harmonic motion. So we know that the kinetic energy and potential energy may be variable, but the total energy is always conserved, right? Thank you everybody for watching this video.